So children, next topic is current loop as a magnetic dipole, and this topic we have already done in the previous chapter, where this is the current loop, and on this axis at any point P, if we have to find magnetic field, then we took this current element on top, IDL. This is the distance position vector R, this is radius, this is x, and if this angle is phi, then this angle will also be phi. Why? Because using Biot-Savart law, dB, the small magnetic field due to that current element, will be mu naught by 4 pi I dl cross r by r cube, and magnitude will be dB is equal to mu naught by 4 pi I dl r sin theta by r cube. That one r gets cancelled, so we get I dl sin theta by r square. Now this theta is the angle between dl and r, and if you see, this dl is, if this is the plane of the, you see, if suppose plane, this is the plane, this is the circular loop which lies in the plane of the paper. This is the center. At the center there is an axis, and on the axis at any point, at any see, I'll keep it here. On the axis at any point you have to find magnetic field. So this point, if I join here, this, so it will be little tilted this side. But you see from top, even if it is little tilted this side, this is perpendicular to this line, tangential line. If it is tilted this side, then also it will be, so anywhere it is tilted like this, from here to here, it is perpendicular to this line. If you come this point, then this line will be tilted this side, and your tangent will be here. If you come to this point, the tangent will be here and the pen will be tilted, this line will be, your position vector will be tilted this side. If you come to this point, this is the tangent and position vector is tilted this side. So everywhere on this, the theta is 90 degrees. So theta is 90 degree always. If theta is 90 degree always, then dB is equal to mu naught by 4 pi I dl by r square. Okay, this is magnetic field. Magnetic field. Now, see direction of this dB. Direction is this side. Now, if I consider diametrically opposite current element here, because of this is a position vector, and you know that the magnetic field is perpendicular to IDL as well as R. So here, for this point, this is R. For upper point, this was R. So perpendicular to R, I made dB. This angle is 90 degree. Okay, and because of that, if this is phi, so this will be phi. Now from symmetry downward, this angle is also phi, and this is our position vector for this point. So 90 degree angle will be this side. So this is direction of dB dash. So this is phi, so this angle is also phi. Now if I write magnitude of dB similar way, I'll get same magnitude, but the direction is different. So now what? So you see, the magnetic fields are in different direction. We cannot add them simply. Okay, so we need to resolve it. So if you resolve it, this can be resolved into this direction and this direction. This direction will become dB cos phi, and this will be dB sin phi. Same way, this will be resolved in this direction and this direction. This will be dB dash cos phi. This will be dB dash sin phi. Okay, now these two, if you see, dB and dB dash are equal in magnitude. Cos phi is same. They are in opposite direction, so they will cancel each other. Okay, so then you will write that for, so they will cancel each other, and these two are in same direction, so they will add up. Then you will say, therefore we can say that for every point on this loop, there is a diametrically opposite point for which the perpendicular component of magnetic field cancel each other, and so the total magnetic field B is actually integral of dB sin phi. Okay, dB sin phi. So in place of dB, I can write down mu naught by 4 pi I dl r square sin phi. So in this, whatever is constant, okay, we can take that out. So for mu naught by 4 pi I, this is a constant. R is also constant, because no matter which point you consider, this R will be same. So R is a constant. So phi is also constant, because this angle phi is constant. For any point on this, phi will remain same. So sin phi can also be taken outside. So mu naught by 4 pi I by r square sin phi integral dl. And so this becomes mu naught by 4 pi I sin phi r square. dl will be circumference of this loop 2 pi a. So into 2 pi a. So from here this pi if you cancel, what do we get is, or suppose we leave this pi here only, what do you get is mu naught by 4 pi I, and then 2 will be there, pi a r square. Sin phi I can substitute. From this triangle you see sin phi will be perpendicular upon this, so it will be a by under root a by r. Okay, so we get mu naught by 4 pi I 2 pi a square by r cube. This pi a square is area, so mu naught by 4 pi I a, this 2 will remain here, upon this will become x square plus a square raised to power 3 by 2. This is the magnetic field, and direction is this way or this way depending on the direction of the current in this loop. Okay, so that means along the axis, magnetic field will be along the axis. Now you see here in this expression, if you have to draw the magnetic, how it varies, magnetic field with x, so it varies this way. As you go out, it decreases. Okay, and now you see this expression which we are getting. If we pi I into a is the magnetic moment of a current carrying loop. So what we get is magnetic field is equal to mu naught by 4 pi, which is a constant in magnetism, into 2 m upon x square plus a square raised to power 3 by 2. Okay, so the similar kind of expression we got in electrostatics, electric field along the axial line of a magnetic electric dipole. There you got 1 by 4 pi epsilon naught 2 p by x square plus a square raised to power 3 by 2. Okay, and in the magnetism magnetic moment along a axial line for a bar magnet when we found, so there we got mu naught by 4 pi 2m upon x square plus a square raised to power 3 by 2. So here on compare, this is for a bar magnet, this is for a electric field along the axial line for a electric dipole, and this is what we found for a current carrying loop. So on comparing, you see it is quite similar. So on comparison, we can say that current carrying loop is also acting like a magnetic dipole.